now that we know how to identify whether or not a salt is acidic, basic, or neutral, we want to spend a little bit of time talking about actually calculating the pH of salt solutions. So we'll do an example. What is the pH of 0.03 molar calcium hypochlorite? And so this example, we're starting to see a lot of the times, a lot of the acids and bases we're dealing with are ions themselves, and how we actually get them in solution is as a salt, right? There's going to be some sort of salt because they're paired with some sort of other ion to get them dissolved in solution. So this is a really common way we prepare acid-base solutions. So what is the pH of 0.03 molar calcium hypochlorite?
So what is the pH of 0.03 molar calcium hypochlorite? So one of the things we want to think about is if we want to know the pH, we know that's really a measure of the acidity. And so, we want to think about, well, what's in the solution that will cause the acidity of the solution to change? And so it's going to come from the calcium hypochlorite. Right? And we know that this is a salt, okay? And so we know we have a salt here, and that salt is going to dissolve. The 2 plus ClO minus, and I balance that for 2. So when I really have a solution of calcium hypochlorite, I really have calcium and hypochlorite. And so the question is, are these things acids or bases? Well, if I'm looking at, start with the calcium, we can see it has no H, so not acid. And it's a cation, so that would mean not a base. The other thing we can see is kind of overall, we can always know that for group 2A, they're neutral. So this thing is group 2A, so it's going to be neutral. So then what about hypochlorite, ClO minus? Well, I know for that, there's no H again. So it's not acid. But it is an anion. So it may be a base. In order to figure out if it's a base, we look to the conjugate. And the conjugate for ClO minus is HClO, which is a weak acid. So HClO is a weak acid. So this thing is a weak base. So ClO minus is capable of doing this reaction where we have ClO minus aqueous plus H2O. That will give me HClO aqueous plus OH minus aqueous. It is a weak base, so it's going to look like this. So functionally, what this problem becomes is a weak base pH problem. When you're dealing with the salt, you do need to figure out what kind of salt it is and what's going on with that. But really, it just becomes a matter of figuring out what it is. They're usually going to be weak acids, either a weak acid or a weak base. And so at that point in time, then it just becomes, well, what's the pH of this weak base solution? Okay? So we know we're going to use an ice table. I got my ICE. So this is one place where we do want to be careful when we're doing salts, because the 0.03 molar is the concentration of the whole salt. So that's the concentration of calcium chloride. But what I really want is the concentration of the hypochlorite. Sorry, calcium hypochlorite. It's 0.03 molar calcium hypochlorite. I want the hypochlorite solution, just the solution concentration of this. And you will then, in this case, there's 2 molecules of that in 1 formula unit, but I want these total things, so there's going to be a factor of 2. So we know that what's going to end up happening, or one thing we need to account for, is that when I have, let's say 0.03 molar of, well, we can try it out, of the calcium hypochlorite, that is equal to 0.03 moles of my solute per 1 liter of solution. And then I can do stoichiometry based off the reaction that for every 1 mole of this, I make 2 moles of that. So for every 1 mole of CaClO2, I get 2 moles of the ClO minus. So that tells me overall I'm going to have 0.06 molar of the actual ion. Because basically I need to account for the stoichiometry. That for every 1 mole of a compound, I get 2 moles of these things floating around. Right? Because it's ionic, they fully dissolve, all of the ions separate out. So we just do need to account for that change in concentration. So when we're dealing with a salt, basically it's a weak base problem, but the wrapper around it is figure out, well, weak acid or weak base, figure out what type of salt it is, and then you also do need to figure out your initial concentration. Because this 0.06 is what goes right there. But otherwise, your ice table is going to work the same. 0.06 minus x, x, and x. And in this case, your Kb, because it's a base, is going to be the conjugate HClO times the hydroxide concentration times ClO minus. And so overall B, your algebra expression is going to be x squared over 0.06 minus x. So this would then be the algebra expression to solve. So basically we just need to do the stoichiometry first to figure out the initial concentration. And then we also just need to start by figuring out what acid-base chemistry is actually happening. But otherwise, it's an ice table oftentimes. Salts don't contain strong acids. They can contain strong base. NaOH is a basic salt. But so here I have Kb is equal to x squared divided by 0.06 minus x. I don't have the pH, so I can't solve for x that way. I do need to do some processing. I am going to make an approximation because it is a weak base, so I can approximate. 0.06 minus x is going to be about 0.06. So I need to figure out what Kb is. This is a common issue with weak bases, where we know that the Kb in this case of ClO minus is going to be Kw divided by Ka of the acid, because we can always only look up those acid Ks times 10 to the negative 14th. And the HClO acid, if we look that up, Ka is 3.0 times 10 to the negative 8. And so I get that Kb ClO minus is 3.3 times 10 to the negative 7. So we can take that, plug it in right there. Do our approximation right there. We end up with the equation to solve is 3.3 times 10 to the negative 7 equal to x squared divided by 0.06. We get that x is equal to the square root, 0.06 times 3.3 times 10 to the negative 7, or that x is equal to 1.4 times 10 to the negative 4. I do need to check my approximation. It's change divided by initial times 100. In this case, that's 1.4 times 10 to the negative 4th, divided by 0.06 times 100, which tells me that I am looking at 0.3%, so pretty small. Just needs to be less than 5, so we're in good shape. Oh yeah, checked off, less than 5. So that means the approximation is valid, which that tells us that's the concentration of hydroxide. Because if we go back, that was our kind of acid-base product that we were dealing with, concentration of that. So the concentration of hydroxide is equal to X is 1.4 times 10 to the negative 4 molar. So then I can get that the pOH would be the negative log of that value. pOH is equal to 3.85. And then the pH plus the pOH is equal to 14. So my pH is going to be 14 minus pOH is equal to 14 minus 3.85. pH is equal to 10.15. So it becomes, a weak base problem like we've seen previously, where the ice table's the setup with the base, you got to figure out Kb usually from the Ka of the conjugate, and then be mindful that you're getting X is not, you can't just take negative log of X to get the pH. You get the pOH out of that, but you can always get the pH from that relationship. So you can figure out those values and you can get those relationships. It's just a matter of figuring out. And this is an important thing, this fact, calcium hypochlorite's not really, if you needed a salt, say, when we go back to things like colligative properties, this isn't necessarily something you would use to change the boiling point or the freezing point of water, because it also affects the pH of the solution, right? And you're changing a lot of things. It will change the boiling point. But really what we want to be focusing on is only affecting that. So this is a base. It has a non-trivial effect, right? This isn't that high of a concentration, and you've moved the pH all the way up to 10.15. You've done a decent amount of change. This is definitely not pure water anymore. And so that is something we want to be mindful of, that our solutions can potentially change things. So that's why we use neutral salts when we want to just have a salt. I just want it to dissolve and be a salt, to affect colligative properties, to change the vapor pressure, do something like that. And we want to be mindful that a lot of salts are either acids or bases, acidic or basic salts, and they change the pH. Now, some salts are neutral, and we use those a lot of the times when we're trying to get, say, an electrolyte solution or play with colligative properties that we've already seen, something like that. It's always going to be a neutral salt.
Participation 1014, question 3. What is the pH of 0.03 molar BaClO42 aqueous? This is the third question on participation 1014, due Tuesday, October 14th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the pH of 0.03 molar barium perchlorate aqueous? That's it. 3 questions on participation 1014. You want to find all 3 of those questions, get them submitted, and get those answers submitted over on Blackboard by Tuesday night. On Wednesday night, the midweek 8 homework is due on active, and on Wednesday morning, we'll do the acid dissociation constants lab on campus, an acid-based lab. And again, we're doing an acid-based lab, or now a lab about acid dissociation constants. You're going to figure out an acid dissociation constant. You'll note there was a video about doing that with a participation question in it. So it's a topic that I think is really important. We might see it later on this semester. Who knows? If you have any questions about anything, let me know. Otherwise, the answers to participation will go live Tuesday night. Otherwise, it's going to do it for me. Enjoy the rest of your day. Bye-bye.